The theory of relativity, redefining the universe. 1. Introduction. The clockwork universe. For over 200 years, humanity thought we had the universe figured out. Thanks to the legendary Sir Isaac Newton, we viewed the cosmos as a just, predictable clock. In this Newtonian world, space was just an empty state where things happened, and time was a universal constant, a cosmic metronome ticking at the exact same rate for everyone, everywhere. Gravity was seen as a mysterious pull between objects, a force that acted instantly across the voice. It was a comfortable, logical, and very human way to see the world, but at the dawn of the 20th century, a few tiny cracks began to appear in this perfect picture. There were things Newton's math couldn't quite explain, like the straight orbit of Mercury or the constant speed of light. The world needed a new perspective. It needed someone who wasn't afraid to ask what if and challenge the very foundation of reality. That someone was a young patent clerk in Switzerland named Albert Einstein. Today we explore the theory of relativity, the moment we realize that space and time are not what they seem. 2. The repel in the patient office. In 1905, Albert Einstein was an world-famous professor with white hair. He was a 26 years old outsider working 6 days a week evaluating inventions, but in his spare time he was conducting thought experiments that would shatter the Newtonian clock. Einstein's journey began with a simple but radical obsession: the speed of light. Experiments had shown that light always travels at about 300,000 kilometers per second, no matter how far you are moving toward or away from its source. To Newton, this made no sense. If you want toward a pole thrown at you, it should hit you faster. But light didn't care. It was the ultimate speed limit. And Einstein realized that if the speed of light is constant, then something else has to give. That something was time and space themselves. This was the part of special relativity. 3. Special relativity. Time is a river. Special relativity introduced ideas that sound like science fiction. Einstein proposed that time is not absolute, instead it's a relative to the observed motion. It measures two-way twins. One stays on Earth while the other travels in a rocket at nearly the speed of light. When the traveler returns, they would find that twin had aged significantly more. To the traveler, time literally slowed down. This isn't just a theory. We see this today with subatomic particles that live longer when they move faster. Einstein also showed that space and time are inextricably linked into a four-dimensional fabric called space-time. And perhaps his most famous discovery from this era was the equations. It revealed that energy and matter are the two sides of the same coin. A tiny amount of mass can be converted into a staggering amount of energy. The universe works no longer a collection of separate but is a dynamic, interconnected playground of energy. 4. General relativity, the fabric of reality. Special relativity were a masterpiece, but Einstein wasn't finished. He spent the next 10 years trying to fit gravity into his new picture. In 1915, he published General Relativity, and it's one of the most beautiful ideas in the history of science. Einstein told us to stop thinking of gravity as an invisible tug of war. Instead, imagine space-time as a flexible fabric, like a giant trampoline. If you place a heavy pulling pole, the sun, in the center, the fabric curves and stretches. Now, if you roll a marble, the earth, across the trampoline, it doesn't move in a straight line because of a pull. It follows the curve created by the pulling pole. That is gravity. Gravity is the geometry of space-time. Matter tells space-time how to curve, and space-time tells matter how to move. This simple realization explained everything, from the path of planets to the path of black holes. 5. The proof bending the star. Einstein's theories were radical and many scientists were skeptical. He needed proof. He predicted that if gravity curves space, then light passing near a massive object like the sun should follow that curve and bend. The perfect opportunity arose in 1915 during a total solar eclipse. In 1919, British astronomer Arthur Eddington traveled to the islands of Principle to photograph the stars near the darkened sun. If Einstein were right, the stars would appear to be in slightly different positions than usual because the sun's gravity were bending the light. When the results came in, they matched Einstein's predictions perfectly. Overnight, Einstein became a global celebrity. The New York Times headline read, "Lights on as killed in the heaven." Humanity has officially stepped out the clockwork universe and into a world where space can stretch, time can warp, and light can bend. 6. Value, from stars to smartphones. You might ask, why does this matter to me? Relativity isn't just for astronomers, it's part of your daily life. Think about the GPS on your phone to give you an accurate location. Satellites in orbit use incredibly precise atomic clocks, but because these satellites are moving fast, special relativity, and are further away from Earth's gravity, general relativity, their clocks tick slightly faster than the ones on your phone, about 338 microseconds a day. If engineers didn't use Einstein equations to correct for this time difference, the GPS on your phone wouldn't be off by 10 kilometers every single day. Relativity is the reason you can find the nearest coffee shop or navigate a new city. But beyond technology, the value of relativity is philosophical. It teaches us that our common sense is limited. It encourages us to look past appearances and seek deeper truths. It reminds us that we live in a universe of inspiring scale and complexity, fostering a sense of curiosity and humility. 7th, conclusion. The cosmic horizon. Albert Einstein's work didn't just give Earth new formulas, it gave Earth a new universe. It opened the door to understanding the Big Bang, the expansion of the cosmos, the mysterious nature of black holes. It proved that the most powerful tool in science is not a telescope or a laboratory, but the human imagination. Einstein once said, the most incomprehensible thing about the universe is that it is comprehensible. He believed that with enough curiosity and courage, we could decode the laws of the stars. Thank you for traveling through space-time with me today. In our next episode, we will bring our focus back to Earth and deep into ourselves as we explore the map of life and the revolution that decoded our very existence, the Human Genome Project. Do you have a favorite great fact about time or space? Let me know in the comments. Keep wondering, and I will see you in the next chapter of our story.
The Fabric of Reality, an exploration of Einstein's relativity for centuries. Humanity viewed the universe through the lens of Sir Isaac Newton. To Newton, time was an absolute river, flowing at a constant rate for everyone, and space was a static stage upon which the drama of the cosmos unfolded. However, at the dawn of the 20th century, a young peasant clerk named Albert Einstein shattered these notions, revealing a universe that is far more elastic, interconnected, and weird than we ever imagined. The context, a crisis in classical physics. In the late 1800s, physics faced a profound contradiction. James Clerk Maxwell had proven that light is an electromagnetic wave that travels at a constant speed $c, approx 300,000 kilometers per second. However, according to Newtonian mechanics, speeds should be additive. If you throw a ball forward from a moving train, its speed relative to the ground is the sum of the train's speed and the throw speed. Physicists proposed the luminiferous ether, an invisible medium through which light traveled, much like sound travels through air. Yet, the famous Michelson-Morley experiment failed to detect this ether. Light seemed to travel at the same speed regardless of the observer's motion. This was the perfect storm that set the stage for Einstein. 2. The process from special to general relativity. Einstein solved the puzzle by reimagining the very nature of measurement. His work evolved into major stages. 1. Special relativity. 1905, Einstein started with two simple postulates. 1. The laws of physics are the same for all observers in uniform motion. 2. The speed of light in a vacuum is constant for all observers, regardless of their motion. To keep the speed of light constant, something had to give. That something was time and space. He realized that as an object moves faster, time slows down time dilation and its length shrinks length contraction. This culminated in the world's most famous equation, $E equals mc $. This formula suggests that energy $E and mass $m are two sides of the same coin, linked by the speed of light $c $squared. 2. General relativity. 1915, special relativity worked for constant speeds, but it didn't account for acceleration or gravity. For 10 years, Einstein struggled to incorporate gravity. His happiest thought was realizing that a person falling from a roof wouldn't feel their own weight. He concluded that gravity isn't a force pulling objects, rather, it is a curvature of space-time. Massive objects like the sun warp the fabric of space and time around them, much like a bowling ball sitting on a trampoline. Applications in daily life. Relativity isn't just a theoretical headache for students. It is essential for modern technology, global positioning system GPS, This is the most practical example. Satellites orbiting Earth move at high speeds and are further away from Earth's gravitational pull than we are due to special relativity. Their fast motion makes their clocks tick slower by about 7 microseconds a day due to general relativity. The weaker gravity at high altitudes makes their clocks tick faster by about 45 microseconds a day. Our engineers must compensate for this net difference of 38 microseconds. If they didn't, your GPS location would be off by kilometers within a single day. Electromagnets, the fact that a moving electric charge creates a magnetic field, is actually a relativistic effect. If you move alongside the electrons in a wire, the magnetic force you perceive is actually the result of length contraction and charge density, changes explained by special relativity. For scientific research and the cosmos in the realm of astrophysics, relativity is the rule book of the universe. Black holes, general relativity predicted regions where space-time is so severely curved that not even light can escape. We have now imaged these shadows of gravity, confirming Einstein's math a century later. Gravitational waves in 2015. The LIGO Observatory detected ripples in space-time caused by the collision of two black holes, millions of light-years away. It was like hearing the universe hum for the first time. Gravitational lensing. Because mass bends light, massive galaxy clusters act as magnifying glasses, bending the light from even more distant galaxies behind them. This allows astronomers to see deeper into the past than ever before. The specific example, the muon experimenter proved time dilation. Scientists look at muons, subatomic particles created in the upper atmosphere by cosmic rays. Muons have a very short lifespan. They should decay long before they reach the ground. However, because they travel at nearly the speed of light, time slows down for them. From our perspective, their internal clock ticks slowly enough that they survive the journey to the Earth's surface. This is a living proof of special relativity. Summary of the journey concept: telestry world impact time dilation. Time moves slower for objects in motion or in high gravity. Precise GPS navigation. Space-time curvature of gravity is the shape of the universe. Prediction of black holes and orbits. Mass energy equivalence can be converted to vast amounts of energy. Stellar fusion, how the sun shines. Einstein's relativity taught us that our intuition is limited by our slow-moving, low-gravity environment. To understand the stars, we had to let go of the idea that time is a universal constant. The mathematical elegance, Einstein's field equations. If the special theory of relativity was a revolution in how we perceive time, the general theory of relativity was a revolution in how we perceive the geometry of the world. At its heart lies a set of equations of breathtaking beauty and complexity. The Einstein field equations EFE either core philosophy, geometry versus metaphysicist John Wheeler famously summarized these equations in a single sentence: matter tells space how to curve and space tells matter how to move. In Newtonian physics, gravity was an invisible string pulling objects together. In Einstein's math, gravity is replaced by geometry. The field equations are the bridge between the distribution of energy, matter, light, pressure, and the curvature of the four-dimensional fabric of space-time, e. Deconstructing the equation, the standard form of the equation is often written as $G_mu nu plus lambda G underscore mu nu equals frac 8 pi G COT underscore mu nu $. While it looks like a single line, it is actually a system of 10 highly nonlinear partial differential equations. Let's break down its components. 1. $G underscore mu nu $, the Einstein tensor. This represents the curvature of space-time. It is derived from the Ricci tensor and the Ricci scalar, which describe how volumes change and warp in the presence of mass. 2. $G underscore mu nu $, the metric tensor. This is the ruler of the universe. It defines the distance between 2 points in space-time. Without the metric, we cannot measure anything. 3. Lambda $, the cosmological constant, originally added by Einstein to allow for a static universe. It is now used to represent dark Energy, the mysterious force causing the expansion of the universe to accelerate. 4. $T_mu nu dollar, the stress energy tensor. This represents the source of gravity. It includes not just mass, but also energy density, momentum, and pressure. 5. Frac 8 pi GCF $, the coupling constant. This term dictates how stiff spacetime is. Because $C$, the speed of light, is so large, this constant is incredibly small, meaning it takes a massive amount of energy to warp spacetime even a little bit. 3. The mathematical miracle, the beauty of these equations lies in their covariance. This means the laws of physics remain the same regardless of which coordinate system you use. Whether you are falling into a black hole or sitting on a park bench, the math holds true. Furthermore, these equations naturally contain the law of conservation of energy and momentum through a mathematical identity known as the Bianchi identity. The geometry of the universe itself ensures that energy is never created or destroyed. It was a moment of pure mathematical harmony that convinced Einstein he had discovered a fundamental truth of nature. For solving the unsolvable, the Schwarzschild solution, Einstein initially thought his equations were too complex to be solved exactly. However, while serving in the German army during World War I, physicist Karl Schwarzschild found the first exact solution. He modeled the spacetime around a perfectly spherical, non-rotating mass. This solution led to the discovery of the Schwarzschild radius, the mathematical point of no return. If you compress any mass like the Earth into a small enough volume, the curvature becomes infinite. This was the mathematical birth of the black hole, from math to the Big Bang in the 1920s. Georges Lemaitre and Alexander Friedmann applied these equations to the entire universe. They found that according to Einstein's math, the universe could not be static, it had to be either expanding or contracting. This prediction, derived purely from the beauty of the field equations, was later confirmed by Edwin Hubble's observations, leading to our modern understanding of the Big Bang. Part 3. Applications in modern science and cosmology. While the mathematical framework of relativity provides the rules, its true power is revealed in how it explains the most extreme phenomena in the universe. In modern cosmology, Einstein's theories are not just historical milestones. They are active tools used to map the history and the future of the cosmos. The enigma of black holes. General relativity predicted the existence of regions where gravity is so intense that nothing, not even light, can escape. For decades, black holes were considered mere mathematical curiosities. Today, they are at the center of astrophysical research. The event horizon, this is the point of no return, calculated using the Schwarzschild solution. It represents the boundary where the escape velocity exceeds the speed of light. Visualizing the invisible, in 2019, the Event Horizon Telescope (EHT) captured the first ever image of a black hole shadow in the galaxy M87. The glowing ring of gas and dust spiraling into the abyss perfectly matched the predictions made by Einstein's equations over a century ago. This confirmed that even in the most extreme conditions, general relativity remains our most accurate description of reality. 2. Gravitational waves, a new sense for humanity. Of the most profound predictions of general relativity was that violent cosmic events such as the collision of two black holes would create ripples in the fabric of space-time itself. Einstein himself doubted we would ever be able to detect them because they are unimaginably faint. LIGO and the first detection in 2015. The Laser Interferometer Gravitational Wave Observatory LIGO made history by detecting these ripples from a merger of two black holes 1.3 billion light-years away. Multi-messenger astronomy. Unlike traditional telescopes that see light, gravitational wave detectors allow us to hear the universe. This has opened a new era of astronomy, allowing scientists to study dark objects that do not emit light, and to peek into the earliest moments of the Big Bang. The dynamic universe and dark energy. General relativity changed our understanding of the universe's history. The Friedmann equations, derived from Einstein's field equations, provide the foundation for the Big Bang theory expansion of space in the 1920s. Edwin Hubble discovered that distant galaxies are moving away from us. This means the universe is not a static container, but an expanding balloon. The cosmological constant and dark energy observations in the late 1990s showed that this expansion is actually accelerating. Scientists attribute this to dark energy, which is mathematically represented by the cosmological constant $lambda in Einstein's equations. This constant, once called his biggest blunder, has become the cornerstone of our understanding of why the universe is flying apart. For gravitational lensing, mapping the dark universe Beke's mass, curves space-time, a massive object like a cluster of galaxies can act as a giant magnifying glass, bending the light from even more distant objects behind it. Einstein rings, this effect creates distorted, magnified, or even multiple images of the same distant galaxy, often appearing as Einstein rings. Finding dark matter. Since dark matter does not emit light, we cannot see it directly. However, we can measure its gravitational pull by using gravitational lensing to see how much light is bent by seemingly empty space. Scientists can map the distribution of dark matter across the universe, revealing the invisible scaffolding that holds galaxies together. Summary of applications. Phenomenolativics basis scientific value black holes infinite space-time curvature. Testing physics at the limit of reality. Gravitational waves ripples in the space-time fabric observing events that produce no light. Big Bang expansion dynamic solutions to field equations understand the origin and fate of the cosmos. Gravitational lens.
Was that even for? Was you playing your games? Was you really bored? No. I really should've known. Be with anime till we hit a red light. Then I see the signs. Oh, after all that time, it's just it for us. You don't wanna try. Thought your love was real, but it never was. No, you can't decide. We were sparks on quiet streets, two hearts finding where to meet. But life pulled us apart, left me talking to the dark. If I called you tonight, would it feel the same? Or have we both moved on to different names? Take me back to the start, before the quiet and the scars. When the world felt small and your hands felt warm. Take me back to the start, if only for a moment. I've been up since 3, scrolling back where we used to be. Half truths in this late night chat, both of us knowing what a lie that. Funny how we talk like we're fine, but your name still lives in my rhyme. Take me back to the start, before the quiet and the scars. Take me back to the start, before the quiet and the scars. When the world felt small and your hands felt warm. Take me back to the start, if only for a moment. If only for a moment. If only for a moment. Take me back to the start, before the quiet and the scars. When the world felt small and your hands felt warm. Take me back to the start, if only for a moment.
All this time, I've been holding on so tight, 'cause all that I do was easy to use. So call my time, but you weren't really mine, just something to do. Thought I never knew. No surprise, but nevertheless, I'm still stuck in self-defense. No surprise, but nevertheless.
hanging on, walking tall. Some days I got no use for it all. Working hard, making less. Some days are bad, bad at best. Foolish notions, foolish lies. I set to thinking I could make something of me, playing every game except the lottery, serving everybody else and told myself I'm free. Misery is a showy state of bad company. Foolish notions, foolish lies. Foolish notions, they cut me down to size. You came along and lifted me up. The going got tough, but the tough got some love. Foolish notions, foolish lies. Foolish notions that made me wanna cry. Foolish notions, foolish lies. Foolish notions, well I said goodbye. Hanging on, walking tall. Some days I got no use for it all. Working hard, making less. Some days are bad, bad at best. Foolish notions, foolish lies. I set to thinking I could make something of me, playing every game except the lottery, serving everybody else and told myself I'm free. Misery is a showy state of bad company. Foolish notions, foolish lies. Foolish notions, they cut me down to size. You came along and lifted me up. The going got tough, but the tough got some love. Foolish notions, foolish lies, foolish notions that made me wanna cry. Goodbye.
tongue when we're talking about what I need. Think you're the silent type, but that ain't what I like. I need a man who knows how to speak, so talk to me. Yap on the phone with your daddy till dawn, fishing with your buddies, going on and on and on. Those fish hear more than me. Cat gets your tongue when we're talking about what I need. Think you're the silent type, that ain't what I like. I need a man who knows how to speak. Oh, you think you're the silent type, but that ain't what I like. I want a man to keep me company and talk to me. Baby, won't you talk to me?
Oh yeah, 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 oh yeah. Hey there, what you drinking? 2 shots, let's pour it up. I know what you're thinking, but tomorrow won't come for us. This life that we're living, ain't never gonna give it up. Double shot for the gifted, and one more for us. There you go, drink it up. All this love in a cup. Yeah, we go slow, we go fast. Yeah, we can't get enough. We stay all day, all night, living in paradise. Remember, you don't get it twice. The time of your life. This is the time of your life. Remember, you don't get it twice. The time of your life. Don't look at the past, no, we're not going that way. Oh, now make it last, make it last to the break of day. No matter what people say, live life in a fast lane. Double shot for the gifted, triple shot for the pain. There you go, drink it up, all this love in a cup. Yeah, we go slow, we go fast. Yeah, we can't get enough. We stay all day, all night, living in paradise. Remember, you don't get it twice. The time of your life. This is the time of your life. Remember, you don't get it twice. The time of your life. Remember, you don't get it twice. The time of your life. first sparks on quiet streets, two hearts finding where to meet. But life pulled us apart, left me talking to the dark. If I called you tonight, would it feel the same? Or have we both moved on to different names? Take me back to the start, before the quiet and the scars. When the world felt small and your hands felt warm. Take me back to the start, if only for a moment. I've been up since 3, scrolling back where we used to be. Half truths in this late night chat, both of us knowing what a life at. Funny how we talk like we're fine, but your name still lives in my rhyme. Take me back to the start, before the quiet and the scars. Take me back to the start, before the quiet and the scars. When the world felt small and your hands felt warm. Take me back to the start, if only for a moment. If only for a moment. If only for a moment. Take me